All right, this demo paper is rrSDS, towards a robot-ready spoken dialogue system. I am Casey Kennington. Along with Daniele, Lucas, Jake, and David, we worked on this dialogue system that we are demoing today. And we're all part of the computer science department at Boise State University. First, I want to talk about the requirements. Research in spoken dialogue system has advanced considerably in the last decade, but it's not enough just to put any spoken dialogue system onto a robot and expect everything to work. And these are the following requirements that make it harder. One is it needs to be modular. End-to-end dialogue is great, but SDS modules need to connect to and be informed by robot modules. It also needs to be incremental, and that processing needs to happen very quickly, as much as possible, as early as possible. Can't wait for verbal ping pong. It needs to be very fast. 3 is multimodal, input from more than speech. Sensors, robot cameras, all kinds of things need to come into the system to so it can make decisions about what to do next. Distributive means all these modules often individually take a lot of processing power. So we sometimes need to put different modules on different machines, like speech recognition or language understanding or something. And each of them might require their own GPU. So we need to be able to distribute this processing load and make it work very quickly and easily. It also needs to be time aligned, in that time delays in sensors and modules are accounted for. Like speech recognition might have a 500 millisecond delay, gesture recognition might have a 50 millisecond delay, but knowing what happened at the same time is really important. So those need to be aligned. And it doesn't hurt that it's in Python. Not a requirement, obviously, for SDS with robots, but given the way things are right now, Python is preferred over other languages. For this demo, we're going to try to approach 1, 2, 3, and 4, modular, incremental, multimodal, and distributive. And what we mean by modular is it's not end-to-end. Here's a typical dialogue system. Speech recognition recognizes audio from the microphone, gives you an utterance in terms of transcription. Language understanding gives you some semantic abstraction. Dialogue manager makes a decision and says something. That's your typical dialogue system. You can, of course, jointly model NLU and dialogue management with dialogue state tracking or belief state tracking. But if you want to make this incremental, it makes it much more complicated. Instead of working at the utterance level, waiting for endpointing, it actually is recognizing speech recognition word by word. So the NLU is updating its understanding as fast as possible. And there's ways to deal with this. There's frameworks out there. I'm not going to belabor those. The one we're using is the incremental unit framework introduced by David Schlangen and Gabriel Scanze. And then adding from modular to incremental is then multimodal. So instead of just speech in and speech out, or even just written text in and written text out, we need an object detection. We need lots of other sensors from a camera, from multiple cameras, from infrared, from bump sensors. And we need to be able to integrate those into the system. In this case, this example, we have speech recognition, which goes into an NLU, but then the NLU needs to know something about the world around it. If a robot is observing an object and someone says, get the red one, it needs to know what red means. It needs to know which objects are actually red. So we need a grounded NLU model. So I want to show you an example of our system in action before I tell you what's in it. This is the Misty robot. Misty, and this is this robot right next to me right now. Misty Robotics 2 puts out this robot. Misty Robotics puts out this robot. It's the Misty 2 robot since August 2019. It has some track wheels, arms, some nice sensors above its eyes here, and an OLED face. And all this demo is going to do is someone's going to say, please find something that's red. And then it looks around. So someone already said, find something red. It repeats red, red twice for some reason. And then it looks around a bit. It's feeding information from its camera right up above its eyes here into the dialogue system. And then it says that looks red. And the speech synthesizers on the robot is the thing that's making that utterance. The rrSDS that we have, these are the modules, and I'll go through them one by one. It's built on top of Redico, which is built on the IU framework. So if you're familiar with InProTK, which is written in Java, this is like that in a lot of ways, different in a lot of ways, but really nice, really easy to build on. I was very happy to see this come out last year. Thilo Michael is the one who maintains this, who wrote this originally, and he has a demo also at SIGDAL, and I hope that you watch that. So we build everything on top of that. Everything that we have here is a module inside of Redico. We have a web camera. This built-in mic and Google ASR are underlined because they already came with Redico. we're leveraging them in our system. We also have a microphone array with 6 microphones on it, does point of arrival and can filter out unwanted noise. It's really nice. We have some cloud-based stuff like Azure ASR, object detection, face emotion detection, mask rCNN for object detection also, which is local and written in Python. We have Keras object feature extractor using EfficientNet or VGG19 or Inception v3 or whatever you'd like. And then our NLU is a grounded language understanding component using the words as classifiers model. There's also incremental RASA for NLU. RASA, you're familiar with, is quite well used for chatbots and things, and it could be useful here for a robot. But anyway, we have an incremental version of it for our SDS. OpenDial, written by Pierre Luzon, originally in Java, has been rewritten in Python, and we're using that as the dialogue manager. eSpeak is a speech synthesizer. We don't use it because we're using the onboard robot speech synthesizers, but it exists. And then we have the Cosmo modules, camera, internal states, action, and speech. Same thing with the Misty Robotics, Misty 2 robot. So this is the Cosmo robot, and this is the Misty robot. They have similar kind of look and feel, but though the Misty robot is much taller and its head can move around a lot more, Cosmo is very small, no taller than say a softball. For distributiveness, you can use 0MQ to send messages across different processes or different machines across the network. We can also use a robotic operating system. We tested that with the Turtle Sim, and we use the platform for situated intelligence for logging. This is all tracked with on a Trello board. If you're interested in contributing or want to learn more about these individual modules, send me an email. I'm the first author on the paper, and I'm happy to add you to this. The system that we actually are using on these 2 robots for our demo is the rrSpeaker, the array mic that goes to Google ASR. That gives us incremental word units on the output. And then the robot camera is looking at the scene, but then it's actually the mask rCNN object detector will find a single object and just pick one, kind of not at random, but it'll pick the one that's the biggest one. And then it will move the robot to look at that kind of in the middle of the screen, and then it will use the Keras feature extractor. So it'll take the bounding box around that object and ignore everything else, grab that object, kind of isolate it from everything else in the scene, and then we apply that to the feature extractor. So we have this vector that represents this object, and then the WAC model, when we train it, it learns which features fit to certain words. So if someone said the word red in a referent expression and the object feature extractor had this vector representing an object, it can differentiate between red things and not red things. And it can do this for lots of words that it's been trained on. And it outputs an object match, says, okay, that's a good one or a bad one above a certain threshold. And then PyOpenDial has some decisions it makes. It decides, do I say that's a match? Do I turn and randomly find another object? Do I go towards an object to get a better look at it? So there aren't too many decisions that it's making. It's rule-based at this point, but OpenDial is nice. You can use training data, wizarded data, or offline data to train right now a dynamic Bayesian network or a deep learned model as a POMDP. And of course, there's robot states and actions that are also modules in the bot. But this is our system. Everything logs to the platform for situated intelligence that we can then use for offline evaluation or an offline analysis. Here's the Cosmo robot. Very similar to Misty. Someone says, look for something that's yellow. So it finds an object and it explores it a little bit more. Then it says, huh, not yellow, that looks orange. And then it makes a decision to kind of randomly turn in some other direction to look for another object. And then it sees this object and says, come on, out with it. That looks yellow. Okay. Future work, better integrations with Psi. So we want to be able to program everything in Python, but have Psi do the heavy lifting, and we're working on that because Psi fulfills the time alignment requirement. It's really nice time algebra, great for login, visualization tool, and playback. We also want to add more modules, including language generation. And to show you that this is out there for you, this is on GitHub. So there's a URL to this in the paper. So please help us out with this, and we hope that you find it useful.